All right, welcome back, everybody. Sorry to repeat myself. We left off last time talking about the gas laws. We have um, Boyle's, Charles, Gay-Lussac, and the combined gas law is what we talked about last time. Today we're going to be talking about Avogadro's law and the ideal gas law. So you should have your paper pretty much filled out. This is page 17 in the practice problem homework packet. It has every little note you'd want to put in here, you can put on there. So anyway, so last time we talked about these, and we talked about Boyle finding that pressure and volume had what was called an indirect relationship, meaning if the pressure goes up, the volume has to go down. So that's what we call an indirect relationship. And they are proportionally indirect. So meaning if you double the pressure, you'll half the volume. If you quadruple the pressure, you'll have a fourth of the volume. So they're directly proportional or indirectly proportional. For the Charles and the Gay-Lussac's law, we have a direct relationship, meaning they go up together. But not when temperature is degree C. Only when temperature is in Kelvin do we see the directly proportional relationship here. If you double the volume, you double the temperature, or if you double the temperature, you double the volume, double the pressure, double the temperature. However, they weren't seeing that with degree C, and of course, degree C has problems like negative temperatures and all that. So we need to use the temperature scale Kelvin. And remember, you can write that down here in your box, in the temperature box. That Kelvin, which is just K, it's not degrees Kelvin. Doesn't matter if you write it, but just if you want to be accurate, is degrees C plus 273. Or degree Celsius is Kelvin minus 273, because all Kelvin did was reset the scale. Instead of 0 being the temperature water freezes, he made 0 what's called absolute 0, which makes it so that there's absolutely no kinetic energy, so 0 temperature. That's what he did there. So that's what we went over last time. The last thing we talked about right at the end there was the combined gas law, which is if we can just combine all these three laws together, if the only thing that's not changing is the amount of gas, like we're basically doing this inside of a sealed container, but we're changing the pressure, we're changing the temperature, we're changing the volume. This would be like if you were thinking more about terms of the weather outside. Sometimes the amount doesn't really get into it because you're talking about the entire atmosphere, and the entire atmosphere is basically stagnant. So this is PV equals nRT. Or sorry, the combined gas law, which is P1 over V1 over T1 is equal to P2 V2 over T2. As you can see, it's just a combination of these three laws. So remember that we talked about gases and how they are measured by four things: pressure, volume, and temperature, and amount. And so far, amount has been held constant every single time. So today, we're going to talk about Avogadro's law. Your book calls it Avogadro's principle, if you're following along in the book. 14, section 2. Avogadro's principle, okay, is he was the guy who invented the mole, but his big deal was that he was interested in what happens to N. N is the amount of gas. Okay. So what's going on with N? So what he decided to do is Avogadro decided to do all of his experiments at STP. And remember that STP is standard temperature and pressure. Standard temp, which equals 0 degrees C, which is 273 Kelvin. And standard pressure, which is any of those pressures. So 1 atm or 760 mmHg or 760 torr or 101.3 kPa or whatever. So what Avogadro did is he made sure that the pressure and the temperature were constant at STP. And what he did is he filled up a bunch of gas chambers, and just for the sake of drawing purposes, I'm going to say they're balloons. And if every single one of these balloons was at 273 Kelvin, and the pressure inside the balloon was 1 atmosphere, then what he noticed was that every single one of these balloons had the same volume. And that volume was 22.4 liters. So it didn't matter what type of gas you had, they all behaved this way, this ideal way, that you had 1 mole of gas inside the balloon, they would all take up the same volume. Now, through math, they were able to figure out what the mole was based off of the mass of the balloons. For instance, say this was an oxygen-filled balloon, it would have a 32.0 grams mass. Say this, for instance, was a methane balloon, it would be a mass of 12 plus 4, which is 16 grams per mole. So, and then of course, if this was, say, something as simple as like helium, then we would have a 4.0 gram balloon. But their temperature, their pressure, their volume, and their amount would all be the same. So what Avogadro found, you guys are like 15 minutes late, man, come on. What Avogadro found was that all gases behave the same way. They all take up the same amount of space as each other. And the only thing they're really dependent upon is the amount of gas inside the balloon determines the pressure inside the balloon, the temperature inside the balloon, all those kinds of things. So his discovery was not called the mole by him. He's called it a volume, a molecular volume, which is where the mole eventually comes in, because that's a German word for molecular. So 1 mole of gas is equal to 22.4 liters at STP. Even though he found a direct relationship with volume and amount, you could use this as the equation for Avogadro's law. However, remember that all gases share V1 and N1 in common. So we don't need this. 22.4 liters over 1 mole. So we can find V2 and N2 at any time because of this universality, or what's called the molar volume of a gas. Just like molar mass, we have molar volume. But unlike molar mass, where you had to go to the periodic table and add them all up like we did here, you can just look at the molar volume. Or sorry, they're all the same because they all take up the same space. So that's what the PowerPoint says here. It talks about Avogadro and Gay-Lussac doing different experiments, getting different molar ratios. says add examples because I don't use this much anymore. Then we talk about Avogadro's law, where he was holding the temperature and pressure constant, and he was able to discover the number of molecules inside the balloon in what he called one of his molar volumes. And then, of course, I wrote that down. 1 mole of oxygen equals 6.02 times 10 to the 23rd molecules. And it weighs 16 plus 16, because remember, oxygen is O2. So that means it weighs 32 grams. Well, because it's a mole, then we also then have 22.4 liters. So any gas, no matter what, contains 22.4 liters of gas. So now we can treat it like a stoichiometry problem. We can add it to our little roadmap. If you guys remember, the roadmap was we had grams over here. You don't need to talk. Everyone's muted when you come in. Grams come over there. We have moles right here. And then we had molecules over here. If you guys remember this from last unit, this was the molar mass, was our road that we used to go from there to there. And if we were going this way, we're multiplying. If we're going this way, we're dividing. And right here, to get from there to there, we have 6.02 times 10 to the 23rd. Well, now we have another road we can take. It's still division to go towards moles. Still multiplication to go away, but now we have liters. And those liters, that conversion factor is 22.4. As long as you're at STP. So now we can add that to our little conversion factor thing. So now if a question asks how much gas is in there, well, we can just use the volume of the gas to figure out the amount based off of this little conversion factor. So I'm not a robot. Post attendee Zoom. Go away. All right. If we go to your homework packet, today's work corresponds with 7, 10, and 11. So let's go to page 7. We're not going to do the collecting gas over water because we're just kind of taking it easy. So as you can see, we have Avogadro's law questions here that asks us to calculate the volume of this many moles of a gas, or to calculate the moles of a gas if we have this many liters. Well, remember that we now have our conversion factor that 1 mole equals 22.4 liters. So if we use that as our conversion factor, we can just do a conversion like we did in the previous example. So we have moles, and we have moles. So for every 1 mole, we have 22.4 liters. So that's how we figure out how many liters this thing will be. Go down here to our calculator, and we'll move our calculator out of the way. 5.8 times 22.4. So a gas, 5.8 moles of a gas, in this case hydrogen, will take up 22.4 liters as long as we're at STP. And so if we look at our little drawing here, let me get rid of my annotations here. Okay, there we go, eraser. If we look at our little roadmap here, okay, we have going from moles to liters, it tells us to multiply by 22.4. And that's what we did on the homework. We multiplied by 22.4. So I'll just take a snapshot of it. And then we got the answer, which I've clicked off, but all right. I'll just do it again. 5.8 times 22.4. 130. We'll just round it up. So this is 130 liters. So if we had a balloon that contained almost 6 moles of hydrogen in it, it would be 130 liters. But what's cool about Avogadro's finding is that it doesn't matter what gas it is, they would all be 130 liters. We would know they were different because they would have different masses. And there's a really cool video by one of my YouTubers I like, Cody's Lab, where he kind of shows different balloon filled up with Cody's Lab. There we go. He has different balloons filled up with different gases. And he kind of throws them around to see how they interact. You know, how a balloon kind of floats through the air. Well, what if you put like a really, really heavy gas? Would it just act like a ball? And the answer is, yeah, that's exactly what happens. Let me find that video for you. He's got a bunch of cool videos on the ideas of gases. Anyway, I'll look for those. I'll post them in the videos section. But if you haven't checked out, if you want to do like interesting sciencey videos, Cody's Lab has a bunch of cool ones on there. So let's get back to it. Homework assignment. All right. So if we went from moles to liters, we multiply by 22.4. So if we're going backwards, we're going to divide by 22.4. So in this case, our conversion factor will be for every 1 mole, there's 22.4 liters. And so we'll just do 89.6 divided by 22. Divided by 22.4. 4. So this is 4 moles of gas. So what's cool is any balloon that would be this size, a 90-liter balloon, would have 4 moles of gas in it. Pretty cool. Again, the only way you'd be able to tell them apart is if they had like a weird smell, which again, we don't want to just smell random things. Or if we picked them up, because the light balloons would want to try and float away. Oxygen is about as dense as air, so it would be pretty neutrally buoyant. It'd be kind of cool. It'd just kind of hang there. Hydrogen is super light. As you guys know, that balloon would just float away. But stuff like chlorine's heavy, and so it would sink. All right. Let's get rid of this one here. There we go. All right, now we're going to take a snippet of the next couple problems. So over here, it asks us to calculate the volume, but it gives us grams. So if you look at our situation on here, we are over here now. In the previous problems, we use Rainbow Pen, we were here and we were going down here, And then in the problem, in the next part, we were here and we're going up here. So we were transferring between these two. Well, for these next problems, we're going from grams to moles, and then we're going to go down to liters. So we need to do the conversion grams to moles to liters. So let's take a snapshot so we can write on there. So remember, in this problem right here, we divided by 22.4. And in this problem, we were multiplying by 22.4. Well, for these problems, we have 3 steps. So first off, we're going to have to go from X amount of grams. Got to get rid of grams. We got to get into moles. And then we got to go out of moles and do liters because it wants the volume. Well, this step right here will be different for every single gas depending on what gas it is. But this step will always be the same. 1 mole is 22.4 liters. So the question is, how do we go from grams to moles? And the answer is molar mass. So yeah, coming back, being used again in this next unit. Let's zoom up on this so I can do a better job of writing on it. Remember that what we said was no matter what type of grams we have, we're going to need to use the molar mass. So for every 1 mole, we're going to have a certain amount of grams. And for every 1 mole, we're going to have 22.4 liters. So what is our mass going to be? It's going to be the molar mass. So for this one, we have 72 grams of sulfur dioxide gas. So for every 1 mole of sulfur dioxide gas, we need to find the molar mass. And for this, you'll need your periodic table. So if you forgot it at home, then you just Google a periodic table, and then it'll pop up. I'll put the periodic table I used on the Google Classroom when I go to the school because I have to get it off my flash drive there. The modified one that's got my handwriting on it. Otherwise, it's just blank. I added a bunch of things to it. So anyway, I can do this in my head, but if you can't, that's fine. You don't need Cody's Lab anymore. You just go in here, periodic table. Don't even have to write table. Go to images. Don't even have to download one if you don't want. Pick your poison, whatever one you like here. This one doesn't have molar masses on it, so that's not very helpful. This one doesn't have molar masses on it. That's not very helpful. This looks pretty helpful. Hopefully it's not Pinterest. Here we go. So anyway, we can zoom up. And it's not going to. There we go. Perfect. So sulfur 32.06. Remember that we like to round it up to one number. One number after the decimal. So that's 32.1. And then oxygen 16, and we have 2 of them. So 32 plus 32, 64. So 64.1 grams. And then for every 1 mole of the sulfur dioxide, we have 22.4 liters. So getting out your calculator, boop. We're going to take our original number here, 72 grams. So clear, 72. We're going to divide that by 64.1. And then we're going to multiply that by 22.4. And as you can see, we got a whole bunch of numbers over here, but this is our history. We want that number right there, 25.1. and this is going to be liters. Now let's ask ourselves if this makes sense. Remember, 1 mole of a gas is 22.4 liters. Well, a mole of gas of sulfur dioxide is 64 grams. This is 72 grams. It's a little bigger, and so therefore we have a little bit larger volume. And that's all there is to those. Let's get rid of this and take a snapshot of down here. And then this is just going to be the reverse. So in the case of going from grams to moles to liters, we did grams divided by molar mass multiplied by 22.4. Well, in this case, we're starting off with liters. So we're going to have X amount of liters. And so we're going to get rid of liters to get into moles. And then we're going to get out of moles, and we're going to get into grams because it wants to know how much it weighs. Well, if we look at our roadmap, going from grams to moles to liters was divide by molar mass, multiply by 22.4. Well, now it says divide by 22.4 and multiply by molar mass because we're going that way. We're going to the left. All right, so let's plug in our numbers for every one of these. There's 22.4 of those. And for every one of these, we need the molar mass. So now we just plug in our numbers. In this case, for this problem, we have 50, for our first problem here, we have 50 liters of C2H4. And it always helps to write out everything because in this part right here, it asks us for molar mass, so we need to know what it is. 22.4 liters for every 1 mole. And then for every 1 mole, we need the mass of the C2H4. So looking at our periodic table, carbon is 12 and hydrogen is 1. So 12 plus 1 plus 1 plus 1. Or sorry, 12 plus 12. So 12 times 2, 12 plus 12, plus 4 times 1. So 28 plus 4, or 24, plus 4, 28. So 50 divided by 22.4. That gives us 2.2 moles, and then multiply that by 28. 62.5. Or grams. And that makes sense because, again, look at our volume. Our volume is like twice that of the regular volume. So we're going to have about twice that of this number. But we're actually a little bit more than twice. So we get a little bit more than 56. We get 62. All right. Let's get rid of that. And go over to this last side here. What's cool about Avogadro's law is that we can know the density of any gas based off of this idea of Avogadro's law. Let me show you how. So as long as we know what the gas is, we know its density. So if we can take a gas and we can figure out its density by measuring its mass and volume, we can identify that gas. Why is that? Well, remember that density is equal to mass over volume. So in this case, we don't know the mass, we don't know the volume. All it told us was the identity. So why don't we just assume we have 1 mole of it? Well, if we do that, then we can do the molar mass divided by the molar volume. And the molar volume never changes. It's always 22.4 liters. So basically, if we want to know the density of a gas, all we need to do is figure out its molar mass and divide it by 22.4. In the case of chlorine, chlorine is 35.5 grams per mole times 2. You can see that right there. It says 35.45, but we're going to round that up to 35.5. So that gives us 71 grams per mole. So 71 grams per mole divided by 22.4 liters gives us a density of 3.17. Grams per liter. This is liters per mole. So those cancel, and we're left with grams per liter. So I said chlorine gas would sink because it was heavy. It has a density of 3.17. Well, let's take a look at why I know that to be true. If we were to look at air, for instance, air is mostly nitrogen and oxygen. Nitrogen is 28 grams per mole, and oxygen is 32 grams per mole. But this is like 78%, and this is like 20%. So let's just say the average air is 29 grams per mole. Some people say 30, some people say 20. Let's just say air's molar mass is about 29 grams per mole. So if we do air's density, then that would be 29.0 grams per mole divided by 22.4 liters. So plugging that into our calculator, we get air's density to be 1.3 grams per liter. So as you can see, chlorine gas is like 3 times as dense. And so it would sink in air if you made a balloon of it. It would behave a lot like a ball. Pretty cool. And again, you can watch lots of videos on YouTube that show different gases. One of the coolest ones, I think I showed you guys that in class, was the sulfur hexafluoride. Sulfur hexafluoride is 6 times as dense as air, and you can see there's lots of videos of people breathing sulfur hexafluoride. It will do the opposite of what helium will do. It will make your voice deep. And again, Cody's lab had lots of cool stuff on why your voice changes with different gases. He breathed in different gases. But a pretty big YouTuber right now, or a pretty big YouTuber right now, is doing live science sessions. And you can obviously go watch them. But one of his recent live science session is, why does helium make your voice higher? So there's a cool video if you want to do like a live science experiment on the density of gases, because it relates directly to Avogadro's law. And of course, it's Mark Rober, who does all kinds of really cool stuff. Huge YouTuber for the whole glitter bomb thing. That was hilarious. All right. So that is Avogadro's law. You can now have that on your little cheat sheet paper you have there, where Avogadro's law, it relates the volume and the amount of gas. So we have some interesting information now. And let's take a look at the other parts of your homework here to see what I'm talking about. So last time we talked about combined gas law. And as the last thing we talked about. And we did some examples from page 6. Page 7 also has combined gas law problems on it, as well as page 11. So first off, how do we know we have a combined gas law? Well, on page 7, it tells you combined gas law. But the most important thing to do is to make a list of all the pressures and temperatures and volumes and amounts, and then decide which law you have. Combined gas law is going to be the most complicated of them because it's going to have the most stuff in there. Let me show you what I mean. So if we look here, we have this problem. We have 50 milliliters at standard conditions becoming 43 and 750 mmHg. This here's a volume. That's volume 1. Standard temperature and pressure is temperature and pressure 1. Remember that STP is 273 Kelvin, and the P is in 1 ATM. In this case, we're going to want to change it to mmHg. So that means this is T2, and this is P2. So what this problem wants us to do is it wants us to decide what's a good equation to use. Well, you'll notice that the problem has everything in it except for amount. Doesn't mention moles anywhere. And it has volume, temperature, pressure twice. It wants to know what is the new volume if we change everything except for the amount. So for all these problems, if you want to skip the algebra step, you can just follow me. You're going to take this guy and put him up here, and you're going to take this guy and put him down there. So that's going to give us volume 2 is pressure 1, volume 1, temperature 2, all over temperature 2, pressure 2. So now we have a setup to find volume 2, which is what's missing here. Notice how it says calculate the volume. It says dry gas because, again, sometimes water gets in there, but we're ignoring that for now. We're going to plug in our numbers. Pressure 1 was STP, so that's 1 atmosphere, but that's a bit pain in the butt. So remember that all these guys are equal to each other. So if we have 1 atmosphere, we also have 760 mmHg. So since our problem uses mmHg, then why don't we just use that, 760 mmHg. Volume 1, 50 milliliters. And then temperature 2 is 43 degrees C. So we need to change that. Remember that Kelvin is equal to degrees C plus 273. So we're going to add the 43 to that. So the Kelvin is going to be 43 plus 273. For those of you who want to use a calculator, bust out that calculator. 43 plus 273. 316. So then we have 316 Kelvin. Bad K. Now we're going to divide that by temperature 2, which is 0, which is 273 Kelvin. And we're going to multiply that by pressure 2, which is the 750 mmHg. Now, I know you probably don't want to write all these units, but it really shows you how you're going to get the right answer when you do. Remember that this question is asking us for volume 2, and you'll notice that mmHg and Kelvin are going to cancel each other because they're on the top and the bottom. And the only one left is milliliters, and milliliters is what measures volume. So you know you're going to be able to do this right, as long as you do order of operations correctly. So what do I mean by that? We need to put these in parentheses. So in our calculator, parentheses 760 times 50 times 316 parentheses equals divided by parentheses 273 times 750 equals 5.9. Milliliters. Did I do that right? 760 times 50 times 316. Oh, that's what I did. 316. Yeah, divided by 273 times 750. 59. That's what I knew. I knew I did that wrong. See, always check your answer. Now, why did I know I did that wrong? Because think about the logic. Remember that the pressure, volume, temperatures all have indirect and direct relationships. And so as you can see, our pressure going from 1 to 2 didn't change very much at all. It went down a little bit, which should make our volume go up a little bit, but again, not very much at all. The big thing was the change in the temperature. The temperature went up. It went up from 0 to 43. So an increase in temperature should also cause an increase in volume. So our answer should be bigger than 50. So getting 5.9, it was obviously wrong. So I knew I hit some wrong button. So went in, forgot. I probably did 75 instead of 750. But does this answer make sense? Yeah. Pressure went down a little bit, should make volume go up, but again, not very much. And the temperature went up a little bit, should make volume go up, but again, not very much. So our answer is 59, not very much bigger than 50. So why did I do that? Well, I showed you that for review purposes, but also we now can make a new combined gas law. Now the combined gas law is still just P1, V1, T1. Equals P2, V2 over T2. This is still the combined gas law. But remember, Avogadro came in and said, hey, there is a direct relationship between volume and amount. So what if we plug that in to the combined gas law equation? Now we have a scenario where all four aspects of a gas's measurement can change. But here's what's cool. Remember that in Avogadro's law, we could always just set gases. Let me get rid of that. To 22.4 is equal to 1 mole. So if V1 and N1, if we just substitute those for the molar volume of gas, then we don't actually have to measure those two things. But wait, didn't this occur at STP? And if this occurred at STP, that means we also know this, which is 1 atmosphere. And we know this, which is 273. So now, with the new combined gas law, these numbers are always going to be the same for any gas. And so because these things are never going to change, we call those a constant. So they gave this the name, the ideal gas constant. If you have 1 mole of a gas at STP, it will take up 22.4 liters. Well, if we put that into our combined gas law now, that means this never changes. So we can rewrite this. Instead of PV over T and N equals PV over T and N, we can delete this and just write the constant R. And since we're not going to be measuring 2 states, we're just going to be measuring 1 and comparing it to this ideal condition, which we already know the numbers of, we can drop the 2's. So now what we have is R is equal to pressure volume over N times temperature. And because this was done back in the day of printing presses, to get rid of this annoying printing thing, they did some basic algebra, multiplied both sides by NT, to give us pressure volume is equal to nRT, the ideal gas law. The ideal gas law is amazing because now we can find a pressure, a volume, a temperature, and an amount for any gas as long as we know 3 of the other criteria. You have that balloon there. You want to know how much gas is in that balloon? Measure its pressure, measure its volume, measure its temperature. Boom, you can find the amount. If you have a mystery gas, like say for instance during our last unit when we talked about finding the white powder in on the dead body, well, what could that white powder be? Well, we used the technique for empirical formulas and molecular formulas to figure out the actual identity of it by finding its molar mass. Well, for this, we could do the same thing. We could figure out the moles in the gas, then simply weigh it, and boom, it would tell us exactly what it was, because all we would have to do was simply just heat the substance up until it became a gas. Pretty cool. A lot of stuff that you can do with the ideal gas law. And in the helpful videos for this, many of the videos love talking about the ideal gas law because it's really just the most useful. Basically, kinetic molecular theory, ideal gas law, behavior of atoms, all these things are going to be really singing the praises of the ideal gas law. And of course, there's a lot about it in the gas laws video as well. So this would have been that lab that I had all those cans for, which is a lab you can try at home if you want. Down here for the ideal gas law, if you want to see it in action, you can go to some of the chemistry at home stuff at the end here. Can't do that one because that one would have been in class. But we can actually look at the gas laws with some cool at-home labs. So if you want to see this in action and you're interested, you can do this. Now, obviously, you won't have an Erlenmeyer flask for the balloon lab. So you would just need to get some sort of bottle that you could put the balloon over. If you don't have an Erlenmeyer flask, you could use a soda bottle, you know, one of the glass soda bottles. It's really cool. You just don't want to boil the water when you're using the glass bottle at home. You just want to heat the water up, put the balloon over it, then throw it in the ice water, and you'll see something really cool take place. And then, of course, you can do the soda lab where you put some water in the soda and then wait for the steam to come out of the soda, then turn the soda upside down in the water, and the soda will crush. There's a cool experiment for you to do. I didn't want to take that away. So if you want to try that, that's fine. You can use tongs, what have you. You don't have to write a one-page conclusion. I just wanted to point out that these could be done at home. You would just substitute glassware for whatever you have at the house. And then, of course, there's some other chemistry at home things you can do. But these have to do with surface tension, and we didn't really go into surface tension, so it's up to you if you want to do that or not. So let's look at some examples of the ideal gas law. By the way, we can now add it to our little cheat sheet here. And you'll notice that I've given R a number, okay? And that's because if R is always 1 atmosphere, 22.4 liters, 273 Kelvin, 1 mole, well, we can just plug that into the calculator. We have 22.4 liters times 1, so 22.4, and then divided by 273 times 1 to give us a number. And so the ideal gas constant is 0.0821 atmospheres, liters, Kelvin, moles. That is the ideal gas constant. That's where it comes from. If you read your book and they talk about R in 14.3, you'll notice that they call it the constant K, and then they just give it the name R there. K is NR or whatever. We now get PV equals nRT. You'll notice that they also give you different values for R, but you'll notice the difference in them is the volume measurement. Because there are different measurements that we can use for volume, we can get different R's. So if you know the different R's, and we're going to use these 3 mostly, but I wrote down on here, on your page, I also wrote the R for PSI, just in case we end up having a problem with PSI in it, we can answer that question. So taking a look at your work, page 10 has the first ideal gas law problems. So again, the secret to all these problems is making a list of everything. So let's take a look at, even though this problem says ideal gas law on it, let's just make sure we know how to tell that. So it says 4 moles of the gas. Let me zoom up. 4 moles of the gas, 5 liters in a 25-degree container, and it says calculate the pressure. And it wants it in atmospheres, and it wants it in mmHg. So there's 2 ways to solve this. First off, let's take a look at our list. We have N equals 4 moles. We have V equals 5 liters. And we have T equals 25 degrees C. I always do that. (25 degrees C). I'm going to add 273 to that to give us 298 Kelvin. Notice that's it. We just have N, we just have V, we just have T, and they want P. If you look at your cheat sheet here, there's only one equation that has only one of each of the 4 measurements of a gas: pressure, temperature, volume, and amount. Well, the ideal gas law is the only one that measures only one of those. So this has to be an ideal gas law problem because we don't have enough information to solve any other type of gas law. So now we can just plug in our numbers. PV equals nRT. And what we're going to do is we're going to rearrange it to find P, so we're going to divide both sides by V. So that means pressure is going to be nRT over V. N is 4 moles. We're going to get back to R in a second, so let's put R there. T is 298 Kelvin. And then volume is 5 liters. So then R, what should we put in here for R? Well, this pressure is being asked to be solved in atmospheres. So when you look at your cheat sheet, find the atmospheres R. This one here has atmospheres in it. So we're going to use 0.08 2, 1. Atmospheres, liters, Kelvin, moles. Now take a look. The moles will cancel, the Kelvin will cancel, and the liters will cancel. And what's left? Atmospheres. And atmospheres is the measure of pressure. So now we just plug it into our calculator. Move it out of the way so we can see what we're doing. We have 4 times 0.0821 times 298 divided by 5. This is going to be 19.6 atmospheres. Now, let's see if that makes sense. This is saying that the pressure inside this chamber is 20 times the pressure at sea level. That's going to be a huge amount of pressure. Remember, that's 20 times 14.7 psi. So what is that? 280 pounds per square inch. Pretty crazy. Well, does it make sense? Well, our temperature is pretty close to standard temperature, which we know would be the volume would be 22.4 liters. So that's not really going to contribute to a very large volume and pressure change. Our moles, though, our moles is 4 moles. And 4 moles normally want to take up 22.4 liters per mole. So that would be 22 times 4, 88, and then 0.4 times 4, 1.6. So that would be basically 90 liters. And instead of having 90-liter container, we have shoved all of that gas into a 5-liter container. And so the pressure inside that chamber is going to be immense. So the answer makes sense. Pretty cool. So I recommend, to help you out with the homework 7, 10, and 11, you check out other videos. There's lots of stuff on there. Khan Academy, the videos I've shown you that you can check out for the ideal gas law. And then, of course, I'm going to come in for our next session because we're not going to do any new content. I'm going to go over more ideal gas law stuff, which is going to be mostly like going over pages 10 and 11. So if you want to concentrate on Avogadro's law for now, that's completely fine. And again, you guys know the quizzes due dates are a little bit far off, so of course you can go slow with the content. Even though we've moved on, this is the next week. You have all the content. It's right there in front of you. You can approach it at your pace. Now, I just wanted to talk real quick about the quizzes. So most of you guys who are in here know what I'm talking about. So this is just for those people who are going to watch the video. When you go to a quiz, if I've given it to the ability to turn it in, you can just hit turn in when you're done. All this is going to tell me is that you're done, okay? So remember that you should take the quiz as many times as you need to get all the points. So you want to make sure you get every single question right. You don't want to just give up when you missed one or what have you. You want to get them all, okay? The amount of credit you get is based off of you getting all of the points, okay? Or getting all of the questions right. And then you can just hit turned in. You don't have to click on anything. You don't have to put anything in there. You don't have to take a screenshot. Just hit turn in. It just lets me know that you're done with the quiz. And then it kind of keeps track of when people are done with the quiz. Because let me show you what I see in quizzes. Quizzes gives me a report, and it doesn't let me go by like date it was turned in. And so I have to like constantly going through it because I just kind of put you guys all in. Here we go, login. I kind of just put you guys in. instead of having 5 periods, I just have one big classroom. So when I go to the reports and I click on this is what it shows me here. If I want to look at the pressure unit thing to see if everybody's done, it doesn't show me like new names. It just kind of puts you in there based off of your score. So I really have to like go in there and be like, okay, well, if you got them all right, you're probably in this score range. So it's a bit of a pain. So if you could use your full name and your period. Things that don't help me at all and don't help you is I have no idea who that is. And then there's another one on here where I'm like, I don't know who that is. Let's see if they've taken this quiz already. That doesn't, Becca. Well, I got 3 Rebeccas, Juliana, like, okay. Which Juliana is that? There's another one. Who's J triple asterisk? Like, I don't have a J triple asterisk, man. So you got to put your name in there and your, if you want to make it easier on me, please put your period in there. Okay. So that's it for today. We've already gone an hour. We don't need to go anymore. Next time, which is going to be on Friday, we're going to talk more about the ideal gas law, and hopefully I'll have some stuff set up. Maybe we can do some like live demonstrations. All right, we're gonna hit stop recording now.